Says I'm live. So, welcome. Welcome to the stream on this frigid in the US Friday. Uh for all of you in the US, uh I'm sorry for the loss of heat in your life. That's why I had to put on the jacket uh today. So, we're a little trying to stay warm. For those of you not in the US, hopefully you are comfortable on this Friday, getting ready for the weekend, all of that nice stuff. Here in the US, it's like, I don't know, I woke up yesterday morning and it was like 20 degrees, uh, which I don't know what that is in Celsius. I guess it's like -5, something like that. Uh, Somebody's gonna come online or afterwards and come in and be like, oh, here's what it is. I probably should like look that up. That's something that I could easily look up. But yeah, it's cold, especially here in Atlanta. Uh, all the jokes about how Southerners can't handle cold. Well, it's true. And it's because the cold is worse here or something. I don't know. But it's cold. It's Friday, and we are talking about PLC topic today. Last week we went through some pretty cool drive stuff with DCCs, and I just realized that I don't have any music on. So I'm going to try and not blow this out of. Hold up 1 second. Let me get all of this set up, because otherwise when I turn this on it will go really loud. Sorry about this. I forgot to get a little bit of music. I know some of y'all have said that the having the music too loud is can't concentrate. But yeah. So hopefully I get this set to where not too bad. Let's see. Let's see what that looks like. All right, that should be it. So there we go. Have a little bit of music, because I can't go without music. I can't concentrate, especially with a little bit of beat. Otherwise, I get distracted. I don't know about you guys, but yeah. So on this Friday, we're getting started. So we're gonna be talking about Siemens PLCs in Portal. If you weren't aware, I dropped a video, kind of an edited video this week that my wife did a wonderful job going through and editing. A little bit of fun just about getting started with TIA Portal and 1200 PLCs. If this is your first time on the live stream, my name is Jason. Welcome. I am the one of the founders and CEO of a little automation company called Alpha Industrial Technologies out of the US, out of Alabama for US people. And yeah, have a lot of different expertise through all of our engineers and everything, but I've got about 20 or so, a little over 20 years of experience in Siemens PLCs, drives, kind of the full product portfolio. But this channel is really about automation just in general, and kind of like improving your topics. Yes, most of the stuff is based around Siemens, but we will eventually talk about, or sometimes we'll just talk about general topics, and I'll kind of like point out, hey, this is a general thing. So if this sounds like something that you are interested in viewing more of, we'll try to have these live streams every Friday. Click that subscribe, and if you're on here now, hit the like button to try to get that out to more people, so that YouTube will help us. Our community is growing. We're about should be hitting 1,000 subscribers here in I guess probably about a month or so. But yeah, that's all for you guys that are clicking that like and subscribing and like all of that stuff, and that gets it more out here. So yeah, so for today we are going to be talking about the S7-1200. In the video that I put out this past week, we really went through just getting started with the basics of Portal. And if you're not familiar with what TIA Portal is, it's a kind of automation package that in one database, in one kind of software package, you could do PLCs, drives, HMIs, networking hardware, all sorts of stuff, all in one package. And so it is really, really an amazing piece of software, and it has come a long way. And so today we're going to be talking mainly about the S7-1200, some of the topics that are involved in it. And yeah, so what I'm going to do is just kind of get started in here, and we're going to go through and just kind of talk about all of this. So I'm going to get sent over onto this other screen. And yeah, if you're coming in and thank you, Brandon. Yeah, so Brandon just is trying to distract me. Brandon is one of the other owners in Alpha, and he's sending me messages on Discord. I'm gonna have to mute this because that's pretty distracting. But yeah, so let's get swapped over to this other screen. And so yeah, so let's start off with, if you've been watching these live streams or you've seen a couple of these, you might be familiar with what this system is. This is already set up, and yeah, if you are unfamiliar with how to set up and bring in hardware and get connected and all of that, well, there's a couple other videos that will get you on this. This was actually set up on another live stream. It was the load sharing live stream. But what I wanted to talk to you and why I brought it up today is because it has a 1200 CPU in it. And this will be kind of the basis of what will be going through today. If you're unaware with kind of the Siemens product line, you have essentially two different types of PLCs. You have S7-1200 and S7-1500, and the 1200 is a brick style PLC, and they call it kind of the basic processor. And as you see in here, or in this project here, you can see that I've named it accordingly. You have the basic system and the kind of the high-tech system. In this particular case, this is a 1500 technology and safety processor, whereas this this CPU is just a basic 1200. So let's go through and let me get pulled up kind of a little bit of an overview of the S7-1200. I'm going to pull this over onto this screen and see if that's going to work. I need to move my head to the other side. And so if you are unaware of kind of the Siemens tools or whatever, one of the best ways to see what options are available for you in your market is the industry mall. And there is another tool that's kind of replacing this. I believe it's called C Portal or something like that. But this is industry mall, and you can get a lot of information about different current products that are available to you. And depending on your region, this website will display different things depending on where you are in the world. For us in the US, we kind of have different options than, say, for a like a Indian or Chinese, because there are different PLCs and products that are available to different markets depending on what kind of import restrictions and export restrictions and things like that that are available. For example, there actually is in India and China a version of processor that used to be the S7-1200, and it's a much less featured version than the 1200, but it's kind of a gap between this logo logic module here and the actual 1200. So and it's essentially the S7-1200 from the previous generation, kind of packaged up, and it's available in India and China, those two markets, just as a kind of a lower cost entry into this world. But today we're going to be talking about the 1200. I get a lot of questions about what PLC is the best fit for me, and it really comes down to how big of the operations that you're trying to do, because the 1200 can do a lot, but it's limited in how much IO it can process and how much programming memory that you have available to you. So as you can see here, you have a core module in this picture, and then you have a couple of expansion modules that expand off on it. It looks like this picture may have a communication module off to the left, and then to the right you have some IO modules. That may be an analog input like an RTD module, and this far right, it's probably a digital input module, something like that. But as you can see, it is expandable. And let's go through, and here's some just kind of general information about everything that's on here. This overview page, if you drill down into your product catalog on IMAL, automation technology, automation systems, somatic industrial automation systems, controllers, basic controllers, S7-1200. Have I ever mentioned that Siemens is the world's largest automation company? There's a lot on this website, and so digging through and finding this information can kind of be a little bit of a pain sometimes. But I've just clicked here on the S7-1200, and it brings up this product information page, and it kind of just gives you a little overview about some of the UL508, CSA, C22.2, like features, communication, all of this stuff. Some of the general overviews, like here, the communication, there things like Profinet, Profibus, master and slave configuration. So this can be as a yeah, so we have a commenter that's asking about essentially whether or not you should go to college to get this sort of information, and the answer is a little bit complicated. If your requirements at the company you are trying to go to, some companies require degrees of some sort just to have any sort of like engineering position. And so the only limitation that I guess you might kind of come across by not having a degree would just be simply if the company you're going to doesn't have that, like doesn't allow or requires a bachelor's degree or an associate's degree, or requires some sort of degree. I will go ahead and tell you, while my college education was very beneficial to me, in terms of automation and PLC, that sort of kind of like knowledge, that did not come from college. There are a lot of associates, and in the US we have kind of two different levels of degrees. We kind of have this associate, which is out of, it's like a junior university level, and usually those are more hands-on, like oriented towards learning how to actually do things. Those sorts of degrees in the US would be something that would be much more beneficial than a 4-year university degree, um, and yeah, so and that sort of like the 4-year university degree, what it taught me was the I guess the best thing that it taught me was how to learn and how to do research and how to kind of like work through the more technical, like difficult details of these processes. How to learn a like program a PLC. There's much more information on videos and channels like this channel and other automation channels that will help you get along into your automation career. Now, if you can't get in the door, then that kind of sucks. I will say my dad is he worked 38 years as an automation engineer and is probably one of the most well-respected engineers in kind of the mining industry. And yeah, he has no degree. He has a couple of certificates from just programs that he took at like at these junior universities. And yeah, now it's kind of a, if you can find a place, if you can find a company that will allow you to kind of build up to the position that you're wanting to be in, then yeah, I would say that a university degree isn't really going to help you that much. It will teach you a couple of classes. You'll get a lot more, I guess, knowledge about some of the more deep topics that we have on this channel, but it's not really going to like it's not really going to help you in automation career. Most of the 4-year universities are going to get you into research and development companies. Like here in the U.S., some of the big the Department of Defense contractors like Lockheed Martin, Boeing, Northrop Grumman, Raytheon, Aerojet Rocketdyne, even places like SpaceX and these other kind of private and semi-private companies that are publicly traded private companies, I should say, but are based around research and development. They require not only a degree, but also a specific GPA in a degree. So, but they're not automation engineers. They're not actually producing most of the stuff that they have. So outside of Atlanta, in kind of the Atlanta area, there is a Lockheed Martin plant that produces the C-130, and the people that design the C-130 all have degrees. Most of the people that build the C-130, which is C-130, if you don't know what it is, it's the big, if you play Call of Duty, it's the plane that has all the gunships and stuff in it. It's that ship, it's that airplane. But yeah, the people that are building that and that are actually designing the processes there probably aren't necessarily degreed engineers. You'll have a lot of experienced technicians that might have a 2-year university degree, kind of like Brandon's talking about with these the geared towards automation. So yeah, if you have a company that's in mind, that you kind of have a goal. When I was in high school, my dream job was to be an engineer for Lockheed Martin, and it's kind of wild to think about that now, because I know for a fact working for Lockheed Martin would drive me crazy. I got an interview there, and kind of like just I realized that it was a blessing that I did not take that position, because yeah, it's it might be fun design, but it's so restrictive in creativity and all of these things, and you're restricted into these different things. And so R&D, like those large R&D companies that require degrees, yeah, it really good benefits, really good pay, but yeah, if that's what you're going for is like stability, then yeah, even in that, there once you get to a certain level at one of these um, companies, then yeah, it it's stable. But yeah, I personally, yeah, my it's where you want to go. That's the answer to your question. And yeah, so getting back to kind of hopefully that answered your question, and hopefully just kind of could guide you a little bit in that. But as far as like getting back to the hey, that's a possibility. We have some in our network of engineers. We have an engineer that has done contracts and worked on projects with us that is in, I think he's in Poland. So we definitely are. There's the community that we're building at Alpha, is wide reaching, and we try to not necessarily require degrees, but we require really passion for stuff. So uh, yeah, Bilal there brings up a good point. Um, I know it's very difficult to, especially when you're starting out and you're young and you don't have money and you don't have resources, you don't have connections. It's very difficult to kind of do your own projects. But there are a lot of very low cost ways to enter in and learn these principles of automation that are much more valuable than a university degree. Um, like getting started with like an Arduino, for example, Raspberry Pi, um, these type of projects, and getting that kind of mindset of automation and learning how those lower level topics and how to program and how to work through bugs and like those sorts of things are much more valuable than a university degree, in my opinion, unless you were wanting to go to one of these like high technology research and development companies. Um, and you can get started with an Arduino, or you can buy packs. Let's see if I think I have. Yeah, hold on one second. I'll show you. Ugh, sorry, but like this little guy here, um, is like a seed studio. You probably pull this up so you can see the full screen. We're talking about cool stuff and random stuff now. Uh, wait, so Arduino has a PLC IDE, huh? So like a for ladder logic. So this little pack here, so this Seed Studio, um, this thing is my go-to for kind of like small automation projects. So this little guy here, these are about, I think this pack of 3, I think was like $21 or something. So you're looking at about less than $10 a piece for these little Arduinos, and they come with little wire on headers. And obviously you can get, if you have bigger projects, but most of the time you're just trying to do some cool stuff like turn on and off lights or automate your cat's uh, cat's feeder or something like that. But it's got like the little header pins that you can like solder onto it if you want to put it on a breadboard. Um, but yeah, this little processor is less than $10, and the IDE for it is free, and it teaches you the real fundamentals of interfacing into I/O And honestly, if you know how to use an Arduino, all of the stuff that we'll be talking about today, like with the 1200s and the analogs and stuff like that, you'll have a much deeper understanding if you start from this than if you start from like a full featured, like full blown out, art, like TIA Portal. I started on something that wasn't even as as good as this. Of course, I'm like older, so um, I started out on, and I don't have any of these, but I started out on a pick. Um, what was the first one that I did? I think it was an 8-bit processor. Yeah, so it was an 8-bit um, microcontroller that was pick, and I had to write in assembly language, and so learning to program and do projects with this will make you a much more valuable. Well, yeah, pick 24 is a 32-bit architecture. Yeah, this was like a this wasn't even pick 16. I can't even remember what. Yeah, because I it's so funny. I was literally automating my a Hot Wheels car launcher. That's how big of a nerd I was. So I put one of these little pick microcontroller. Not this. This is a Atmel. Uh, this is like ungodly faster than than what I was like playing with. But yeah, I took and um, automated a Hot Wheels car launcher with a little 8-bit PIC processor that had, I think it was like a 16 pin PIC, so it had like 8 IO or something like that to it. Um, Comparable to like the size of this, but this has so much more on it. Um, but all that to say, when you go from something like this into uh, a, a PLC, you will be, first of all, you'll be grounded into reality. A lot of like these kind of like code camp programmers or whatever, like that go to like a coding boot camp and they're programming on Python. Um, a lot of times you won't actually, you'll learn how to code and write algorithms and write logic like in your head, and you'll learn how to program. But when you interface into a piece of hardware, you actually, like the real world, like you have to with this, um, you can't overlook things like how much current is going through your device, how much, what's your voltage on your inputs coming in, um, the length of cable. It will cause issues like on to like your IO and like all this different stuff. And so it's like, if you're not grounded into that hardware and grounded into the real world, your programs can actually be not only damage equipment, but it could be harmful to people around it. Like I always kind of make fun, but or kind of joke around about like the difference between a PLC and like a drive is the fact that PLCs are just turning on and off LEDs, whereas drives are actually moving things and moving the world. But in a way, that same concept is true in automation. You're not programming an app on a phone that's trying to get people to buy some sort of gym. Like you are actually moving equipment. You are moving things in the real world. You are your code endangers people's lives. I mean, it also improves people's lives. That's the ultimate goal. But if you don't go into the mindset that, hey, this little program change that I'm about to make could literally throw a car across a room. That's how powerful some of the stuff that you may be working with. If you're not grounded in that reality, you're going to run into trouble. And so, yeah, very low cost way of getting into the world. These kind of like Arduino, mini Arduinos. These are like less than $10, and these have built-in USB. They're USB powered, and then you can also power them from like an external source. These are the best, like really good ways to get a lot of experience in automation and get that mindset of where you're going, because you understand how to use one of these, you're going to understand a lot of the stuff that we're kind of talking about with kind of especially the 1200 and the 1500. The 1200 processor has a lot more restrictions just in memory, but just from in general, a in general your Siemens PLCs, they are closer to this little Arduino than they are to your full-fledged like a multi-core like processor like PC, uh, and you can kind of see when people compare like Allen Bradley to Siemens, one of the big differences that you have no connection to if you've never dealt with like an Arduino or a microcontroller is the fact that um, because Allen Bradley are all implicitly tag based, the memory that your programs use, if you're doing a lot of Boolean logic and like just kind of going through and doing like bits, an Allen Bradley program will swell and like get really big just because it's a tag that's called a Boolean. It's not actually a Boolean. It's not actually a bit. Uh, what? Oh, Daniel, what is the question you mustache? Like that's uh, I'm kind of afraid from a question from you, but uh, yeah. Welcome to the stream, Daniel. By the way, yeah. The with what's the size of those programs, because Allen Bradley has a 32-bit tag that represents 1 bit that's a true or a false. Those programs swell. Siemens doesn't do that. Like if you're using a bit, you're actually using a bit. So a Boolean takes up 1 bit. An integer takes up 16. A real value takes up 32. So all of these are all actually much more efficient on Siemens processor because fundamentally it's closer to one of these than it is the laptop that I'm streaming this on. So kind of getting back to the 1200 kind of like architecture is you have kind of a basic built-in IO, and the thing about the 1200 is it can do quite a lot of stuff, and as we kind of go through what it can do, it absolutely you can kind of see that you can do a lot of projects with this. But the biggest restrictions are going to be the number of IO points that it can handle. But even then, it's pretty good, especially at some of the higher end ones. I will say price point, at least from what I've experienced. I'm going to click on this and we'll look at the actual kind of breakdown of the different versions. So, there are a couple of different versions. There are 3 different versions per kind of like level. So you have a 1211, a 1212, a 1214, 1215, and a 1217. So you have these 5 different kind of versions, which represent kind of functionality bumps. And so you can see for the most part, you're getting more program memory and more IO. So the CPU 1211, which I actually have on a little rack here that might be playing with later. It only has 6 inputs, 6 inputs and 4 outputs, and then you kind of go up to 8 and 6, and then 14 and 10 for the top 3. And so for these top 3, the 12, 14, 15, and 17, those really are just differentiated by the IO, or not the IO, the memory. And there are some other differences, like for example, the 17 has an analog output. It has 2 analog outputs integrated. And so you can kind of go from there. From a price point, what I have experienced is this CPU 1211 is in the like $200 range for a processor in the US. And whereas the logos are around like $80, so less than 100. So they're about double the price of a logo. but you actually get a ton of features that will go through. And you also get to program them in Portal. Now, Portal's not free, but there is a basic version of Portal that if you're only programming a 1200 PLC, then you can actually use that. Then you can actually use that basic version. And so, sorry, I realized the music wasn't on repeat, but yeah. So there's a basic version of software that's much less expensive than the TIA Portal license, and I think it's on the order of about. Actually, I have never bought that software. It's much less than the big TIA Portal version, but so yeah, I may look it up later and kind of figure out that, but so yeah, so let's talk about a little bit difference inside the thing, or inside each kind of like version. So each version has 3 different kind of types inside, and so these options, you have a DC-DC, DC, AC-DC relay, and a DC-DC relay. And what this is the first is what your input source is. So a DC, like a DC-DC, DC, and a DC-DC relay use a 24 volt power, like they require 24 volts. The AC-DC relay is if you have a 120, 220 volt system, it has a power supply built into it to power it off of that AC line. That's what those are. And so you have your power supply, your inputs, and then outputs. So DC or AC power supply, and then you only have DC inputs. So you only have 24 volt inputs. And then you have an option for your outputs of whether you would like a DC output or a relay output. Most of the time I use the relay outputs just because most of these are going to be switching AC loads. And if you want to switch an AC load, that's the only thing that you're going to have the option for. So if you're putting this in on like a farm or something to where you're turning on and off some lights, like some lights out there, because these have 2 amp capacity on those relays, so pretty good load. And so for $200 you can bring in this PLC, and you can have four relay outputs to be able to control solenoids, to be able to control slide gates, anything like that's out there. So if you notice, the expansion modules are also pretty big difference. So you have two different versions. So you have a signal board and a signal module. If you can kind of see on this front end here, the signal board will go on, there's this kind of like hidden little box here that you pop off this little cover. And then you plug in an expansion module on the front, and it's kind of like a daughter board that kind of goes off on it. And you can have one of those on this lowest end 1211C. The 1211 can only be expanded by that signal board. It cannot have like the expansion modules that go out to the right. You have to start with the 1212 for that. And the 1212 has a maximum of 2 of those expansions. So we can kind of look at some of the options for IO modules, but you have things like a 16 digital input, you have relay output modules, you have analog input modules, you have RTD modules, you have things like that. And in order to use those modules, you have to have a CPU 1212 or above in order to use that. I've got a couple of these different projects out there that I've used the 1200s on. And as I went to expand, I went with the 1212, and I'm like, oh crap, I'm running out of expansion. And so I've had to kind of like maximize that, that kind of like the signal board and the signal module. And so, yeah, that's a big restriction is the IO count. And again, for a simple project to where you're just wanting to maybe add a little bit of control, because we're going to go through a little bit of thing called iDevice to where you can actually use this as a as an IO device to like another Siemens PLC. So you can use this $200 brick as a expansion module and have built-in IO that's sent back and forth to another CPU, and I'll show you how to do that here in a little while. But yeah, so again, I don't want to get too much in the weeds, but if you have questions about like what are the capabilities of some of these, like be sure to drop them in, drop a comment, drop it in chat. But yeah, there's a couple of restrictions. So it does have 2 analog inputs that we're going to talk about a little bit more in detail here in a second. But they are voltage only, which is kind of restrictive. And so where are the analog inputs? Here they are. So it's only a 0 to 10 volt input on the analog inputs, the built-in analog inputs. If you want current input, you have to get an expansion module or a signal board. So if you were doing 4 to 20, then you are going to need to bring in another expansion board or a signal module, which they have IO. I want to say it's like 2 analog input for the signal board, so it's very restricted. So kind of unless you know for a fact that you just need a very simple project, the 1211 probably isn't going to be what you want. Like I have a 1211 here just to be able to like connect up to and be able to kind of play around with, because honestly, I mean, it's the cheapest one. I would probably go with the 1212, because if you run into wanting to bring in like a 4 to 20 sensor, then you're probably going to want that analog input module on the side. So a good thing to think about that. So yeah, so kind of just going through and looking at all of these. I don't think, so one thing though that is kind of important to talk about is if you're not restricted by the IO, but you are wanting to kind of do something like this, in this system, we're actually doing a load sharing kind of master follower relationship with a basic CPU, so a 1200. I have a 1215 in this one, but that's not even required. You could do load sharing between 2 axes. You could do like a simple winder, like kind of low performance winder application just with a 1200 CPU, as long as you don't have a lot of IO. And you could do it with the 1211, honestly. You would just have to kind of write your code pretty efficiently. And so it can be a Profinet master and a Profinet, or maybe not Profinet, but it can be the Profinet master for 100% for sure. And the kind of like slave configuration is kind of a little bit of an asterisk. The way that it sets up that we're going to do is called iDevice. So we're going to talk about that in a minute. But cool thing about this is it can absolutely control, it can control drives. It can even do technology objects. Now, technology objects on the low end, it's too much for like the 11. Like I think that you wouldn't want to do a technology object on anything, I think less than a 14 if I remember correctly. But technology objects consume a lot of just extra processing power that are specifically used to do those technology objects, and they have a specific kind of space in their memory for it. And on the 1211, it just is so restricted that even if you could, you might be able to do like a PID technology object, but I probably wouldn't do a position controller or anything like that with a technology object on a 1211. I would go up to a 1214 or a 1215. With all that said, you can still do drives. Let me get back this up. And I don't think that there's anything else that will do that comes up here. Oh, so there is one thing on the DC DC. So like the ones with the DC outputs, you do have an option for one of these for what's called a pulse train output. So like a PTO. So you can actually directly control stepper motors with these. And so may eventually do that kind of stepper motor configuration later, because I have done that before with things, and it's pretty cool. So if you have a stepper motor in something that is yeah, so here, so the digital outputs for the DC-DC, you have 400 kilohertz PTOs, and that's, I think that's on all of them. Yeah, so even on the bottom end, you have the 100 kilohertz PTOs. So pretty cool for that. May eventually do something with that, just to show y'all how it's done. Let's see. We're about 45 minutes in. Also, I guess one thing that I will show you, even on the lowest end processor, you have a maximum of 18 HMI connections on all of these. So, and this can be any HMI connection that uses that same bandwidth there. So yeah, so all of that to say, these guys are pretty stinking powerful. They even have, is it on here? Yeah, so all of these, again, we're looking at the lowest end. They have a web server that you can actually ping and hit the IP address if you enable this web server, and you can build your own JavaScript web pages to interface in with the controls, and that is really powerful and really underused, especially if you're kind of starting out and you're wanting to kind of get started with PLCs and getting to learn something. All right, you got to buy a PLC hardware. You got to buy HMI hardware. You got to buy all of, okay, well, this 1211 has a built-in web server that if you were wanting to do some sort of like, I don't know, like a hydroponic setup or something, you could do a basic one with this and even have it to where you could connect into the PLC, have a built-in web server HMI, and it'd be built on, and all you'd have to do is just hit that IP address, bring up an HTML page, and you control lights, timers, all of that sort of stuff. So pretty cool stuff. So let's look at some of the options for communications modules and IO modules. I mean, we won't go too much into it. I wanted to spend about 45 minutes or so on this, but so the IO modules, you have digital, analog, you have some special modules, which so like an IO link master, it can handle 4 IO link connections. There's simulator modules, which have like little switches on them, so you can, if you're building a kind of like test setup or whatever, the simulator modules. Then there's last stream someone started asking about a CWRX, and the CWRX module is a weighing platform, and it's to bring in a calibrated scale head. So if you have these calibrated ANSI calibrated heads, you can actually bring them into this CWRX module and use them weighing functions built into this 1200. Very powerful, very powerful. Communications, I think kind of gone through all of these. Yeah, there's a bunch of stuff here. I guess these the CP1243s are, I guess, the 1 and the 7 maybe. I know this. So the 7 here, they're radios, so it's like cell phone modules. So you can plug into the 1212 and above. You can plug in a cell phone basically, and you can connect up through that cell phone connection. For a simple system, like if you're putting it out, like I don't know, on a station or something that's cell powered, or not cell powered, but like solar powered, and you have a little battery solar powered setup, that you could use this and run this and have access to it, and you could connect up to it. And those cell connections allow you to log into Portal just the same as if you were sitting there plugged into it. Alpha uses a system called Cinema Remote Connect, and some other kind of more complex, higher level security devices to be able to connect up to stuff. But it's really cool, and yeah, these are built into this 1200. Last thing I guess we'll talk about is the fact that there actually is a fail-safe version of this, so an F-rated processor on it, and it is they're just the CPU 1212 FCs, 14 FCs, 15 FCs. So what this gets you is, if you're familiar with the Dynamics kind of onboard safety and the safety rated processors, so I'm not familiar how to like compare it to what is available in other processors, just other brand processors. But with a safety rated processor, you can write functions that are, if they run on the processor, that functionality is rated for safety functions up to PLE, SIL3, things like that. This is a safety rated processor. Now, little caveat is that the onboard IO is not safety rated. So you have to buy a safety rated expansion module to go onto it. So you're sitting there, okay, what is the processor get you, this FC processor get you? Well, the biggest thing, in my opinion, is, see if I can find it quickly. Where is it? Is the fact that it can actually be a Profi Safe Master, which is kind of insane. So I think it's right here. Maybe not. Yeah, it can be a Profi Safe. Profi Safe. Here it is. Yeah, Profi Safe. So it is available as a Profi Safe Master, which is crazy awesome. And what that gets you is, if you've ever heard of the Siemens integrated safety on the Dynamics drives, you can activate those safety rated functions with Profi Safe, which is a safety rated Ethernet based communication protocol, with this safety rated processor. That, I think the lowest end on this, the last time I bought one, is around $650 or so. So you can have a safety rated drive system end to end, with just, yeah, with a 600 less than $700 processor. Now, that's pretty cool. But again, to bring in the signals from the IO, for like your e-stop, you would have to expand it by a module for that. But if you're doing some sort of just kind of like safety rated functions that you're wanting to do inside, and activating those safety rated functions, say, not necessarily autonomously, but you kind of get it. Maybe you have another system and you're wanting to add on this kind of like separate system. You have this Profi Safe communication available to you. So, yeah, so safety rated processor in the 1200, and those have been around for quite some time now. But yeah, price point, I mean, just in my opinion, and for any Siemens sales people in the US or whatever, like, they probably won't like me, but normally for most safety rated systems, you're probably going to eventually move up to a um, 1500. And here's why. Because if you're familiar with safety rated systems, and a lot of times people are trying to reach the performance level Echo, which is the highest rated, other than like nuclear rated. And in order to do that for your inputs, you take up 4 wires per input. And these input cards essentially make it to where at most you're going to get 4 safety rated inputs on an input card. And then all of a sudden you're kind of like running into this situation to where, unless you have some sort of ProfiSafe rated input device that's out there, which by the way, they're expensive, you start to run in this situation to where you run out of IO pretty quickly. And so, yeah, I think the lowest, you end up spending about the same amount, or you might spend a little less for like a very simple like e-stop drive system that you're just trying to trigger an STO on a G120 and you want an e-stop. You might end up, you'll probably end up spending about the same amount than if you just went with like I think there's a 1510, and then a 1510-F, or maybe it's a 1511-F. You're going to spend about $400 or more on the processor, but then you have kind of this expandability that you could kind of expand out a lot more with your IO, to whereas it's a lot more restricted here. So it might work, but you do have the option for that. Really great in drive systems though. So I've talked a little bit about this 1200 processor. Probably talked more than a little bit. I've talked a lot about it. If you have a question, again, just drop it in the chat, or if you're watching this on demand, welcome. If you haven't already, like, subscribe, and we do these every Friday. If you can join in Friday, that's awesome. If your boss is upset about you watching YouTube on it, just look, it's obviously, it's learning, it's continuous education, so just let him know. And if you drop a comment, and I'll get back with you. I'll vouch for you. But yeah, so let's take a look at this system here that we have. So obviously this one has a 1500 and S120, kind of all the advanced stuff in it. But up here, we have a couple of G120s hooked up to a S7-1200. No, that's definitely, so Daniel's got a great question. So a safety rated input is in Europe, and this is really a lot, I mean, for kind of everywhere that's not the US, you have what's called a CE mark, and it is a it's a certification that the equipment will be safe. And in industrial equipment, that mark certifies that if it were to fail, it would also fail safe. And so the fail safe inputs are kind of is what that safety rated input means. Now, a couple of things about that safety rating. If you have a say just a reed switch that's just out there, it's just an open and close, normally like a normally open contact, and so if something hits it, then it will activate this input. So how can that fail? Well, with a normally open contact, how can it fail to sense the danger? So like, say this danger is the fact that this guard is coming up. I'm gonna go full screen here. Say that the danger is a guard coming up, and then now someone has access. So you have a little read switch that's here, and if you have a normally open and have it set to where when you open up the guard, it clicks and it says, hey, the guard's open. That would be what's like a normally open. So it closes when there's a danger. Well, the easiest way for that switch to fail would be it doesn't close. Like the contacts don't actually make up. Maybe you've got a little corrosion on the contacts and it fails to sense that it's actually closed. Well, that input would fail pretty easily. So you say, okay, well, the easiest way to be to make it a normally closed contact. Okay. So normally closed contact, because another way that could fail is a wire could come off of that normally open contact and the gate comes up, it switches, the wire's open, and it doesn't know any different. So there's a lot of modes of failures for that. With a normally closed contact, it's a little bit safer. It has a higher degree of safety because if that wire comes off, then it says, hey, I've either got a failure or it's got an open circuit. So the PLC, you're kind of determining your processing device. It says, hey, it's either open or failed. And so I'm going to go into a safe state. I'm going to put my machine into a safe state. So the meat grinder on the backside of the thing, on the backside of this gate, stops. And so it creates the machine to put it into a safe state. Well, there's a lot of different failure modes, like short circuits, contacts, welding, things like that kind of like the different ways you can miss a danger. A safety rated input, depending on how it is rated, is certified certified a lot of times by TUV, that it can detect up to a certain percentage. Most of the time at the highest rating, the PLE, I think it's like 99.8% of failures it would detect. So a safety rated input is certified to be able to use these safety rated detecting devices, and it be able to actually, if the gate either comes open or something happens with the system, it will be certified to be able to detect that problem and put the machine into a safe state. That's a really long-winded explanation, but that's really what it's doing. It is certifying that if you have the correct type of input the correct type of device and the correct type of input, that it will detect all of these different failures so that you can't accidentally open up a gate and a wire be loose or a wire be welded together somehow and shorting something out, and all of a sudden your worker is able to get their hand into the meat grinder. So that's what that is. And I will definitely do a live stream just on the safety rating, because one of the things that my certification has expired, but while I was at Wesco, I was certified to do what's called risk assessments, and there's a lot of information that's about these type of safety systems that is a little bit confusing. So that is definitely not a dumb question, Daniel. So yeah, so these small, normally the big with Siemens kind of like innovated in this safety realm, because a lot of these the CE mark and these standards that the CE mark comes from, or uses, comes out of Europe. So Siemens is not only just the biggest user, but they're also like a driving force of automation and all of these standards. So they sit on the boards of all of these like TUV safety standards and like all this stuff. So highly involved. So when it comes down to like Allen Bradley versus Siemens, Allen Bradley, I mean, the only reason that they would have to have a CE certified system or be able to meet a CE certified system would be if it is going out of the US. And so the vast majority of Allen Bradley's install base is in the US. So because they have not had to, and when I say they have all sorts of like CE marks and like all this stuff, they have all of that now, but they haven't been born into it. they were not raised in it. They have just known the CE mark. They've just known the safety. And so whereas Siemens has come into the whole ladder logic and tag based structure, Allen Bradley has had to come into the safety rated technology. And so especially if you're an Allen Bradley user, when you hear safety, you think, all right, this is going to be 3 or 4 times the price just because I have to have a safety processor, all of this stuff. But with Siemens, safety rating a system and meeting these TUV standards and CE mark, there's a much lower price point and less of a jump between a safety rating and a non-safe rated. So great question. I'm going to do a whole live stream on just that stuff. But so the fact that you have a safety rated processor, the fact that you have a safety rated processor up here, so you can see all of the yellow. So in your library here, anything that has a yellow in Siemens world means safety. And so it's going to have some sort of safety certification. So you could see here we have the 1212s, 1215s, the different versions, and the fact that you have a small brick safety rated processing PLC is kind of crazy, and it was pretty groundbreaking. I mean, it was a pretty big deal when they put this out, because everything else, in order to get a safety rated PLC with Allen Bradley, you're going to be having to spend thousands and thousands of dollars. I am shook. I've quoted some Allen Bradley processors just as like spares to some of our customers that have them, and it's kind of like blown my mind how expensive some of their processors are. Could also be that my distributor doesn't like me because I'm like always selling Siemens. That could be something to do with it. But anyway, so I want to talk about a couple things. First, I want to talk about a feature called IO device, and it's a way to take like a small, like a CPU 1211, and if you're familiar with kind of like the concept of cloud computing and like the industrial revolution 4.0, like all of these things, you hear the word called edge computing a lot, and essentially you'll have a cloud, some sort of like data repository, then you want to do something on the edge, which you don't want to constantly be communicating back to kind of your central system, and you want to kind of do work on the edge. Well, in an automation world, you may have that. You may not want your main PLC constantly updating kind of like this cell, and you have a little 1200 PLC that's in this cell, and all you're really wanting to do to send back to your main PLC is maybe like a couple of IO, like whatever that may be. Well, there's a couple of ways that you can send information back between PLCs, and the easiest way is to set up one of your PLCs as what's called an IO device. And when you bring in like these G120s, you bring in and you have to select an Profinet controller. So who is controlling the process? Like, who's controlling the information on this bus? Who's kind of like the traffic controller? So what we're going to do is I have over here, and we probably won't hook it up, but I have over here a 1211 DC over here. And I'm going to take and I'm going to bring this into this project here. And all of this is fairly new. They try to protect you to make sure that you understand that there is program protection, safety rated function protection, like all this stuff. You have your project protection, so you can put the actual code behind logic, then you can lock down, or a password, then you can lock down the actual processor behind a password. And then this is kind of like communication from different devices, because if you're not aware, this is a secure connection. When I unclick this, there's some legacy connection stuff, and there's some kind of like nasty access stuff that you have that is available, that, like, for example, I have a video about a SIP programming block that that actually Daniel on here worked with me to help figure out how to use. But that SIP block goes through and acts as a HMI to an Allen Bradley processor, and you can access tags as long as you know what the exact tag name is. You can access tags just as if it was an HMI, and so you can do some pretty crazy stuff with it. If you're interested in that sort of stuff, definitely check out that video. It's in the PLC programming and PLC training playlist. But so we brought in our 1211C CPU, and what we're going to do, I want to set this up as an IO device, because what I would like to do is give this other 1200 access to the IO on this 1200. So I want to kind of use it. Steve, welcome back from Dubai. We're talking all things 1200 today. Good to see you back on the stream. We're setting this smaller 1211 processor up as essentially a remote IO station for this other 1215. But this remote IO station, instead of like an ET200 SP, we're going to actually set it up to where, hey, we can do some edge computing, we can process, we could do some things locally at this PLC. We'll even name this thing our edge PLC. Okay, and we can, so I'm going to name it edge dash PLC. Don't put spaces. Spaces are bad. Don't put underscores. Underscores are bad. Use a dash. So edge dash PLC. And we can process things. We can kind of do our own things, but then we want to give that IO over to our main basic CPU. Kind of use it as an extended function. So what we want to do is we want to click, and if our inspector window, which is this thing down here with the properties, is not open, we can either click this little arrow, bring it up, or if we are a Siemens power user, we just hit Control 5, and ooh, it magically comes up, and we show off, and everybody thinks we're smart. No. But what we're going to do is we're going to go down to underneath the Profinet interface. We're going to go to operating mode, and we're going to check this little box called IO device. And the assigned IO controller, we're going to select as our CPU basic. And it is going to lock us into that, that device. And so if you notice, it already gives us a device number. So we have probably device number 1, device number 2, device number 3. So like on the Profinet, on this CPU basic Profinet network, we are, we're connected up as the third device. Now, what does that give us? it gives us the option now. We're going to save. We give the option now to create what's called a transfer area. And it's going to be a CD. And we're going to now come into this iDevice communication setup here. And we're going to click on this transfer area. And we're going to name it Edge IO. Ooh, what did I just tell? What did I just tell y'all? No underscores. No underscores. So we're gonna call it Edge IO out. And again, this is going to be talking about looking at it from the perspective of the main CPU, because we just created this kind of like remote IO edge device, and it's creating an area that on the main processor is going to be accessible via Q and I memory. It's going to be just the same as like an input or an output. So we're going to call this edge out. Why? Because on our partner, on our CPU basic here, we're going to use this address as we're going to access it via outputs. By default, it gives us the sorry, I'm just fixing the stuff I messed up. By default, it gives us the first available Q memory location. So on our 1215, I think there's like 4 or 5 digital outputs or relay outputs. And so it just gives us the first output as being 2. And locally, we don't have that many outputs. Actually, let's see. Because we don't have that many inputs, I should say. And so our input addresses, we only have like 4 or 5 inputs. We don't have a lot of inputs. So we don't even have a byte's worth of input. So it starts at 1 here. So on our main processor, starts at Q 2.0. And then it will land in our local at I 1.0. Right now we're only sending 1 byte. Let's just bump that up to like so remember, if we want to send a real data, that's going to be 4 bytes. So let's bump that up to like 10 bytes or something like that. Okay. Because we're not actually just restricted to the actual we're not just restricted to the actual IO, because on the edge, we're actually going to be populating this area however we want to. So give it a little bit, give it some bytes, give it a little bit of data, and then we're going to come over here and make the input side of this. And so we're going to make edge dash IO dash in. Oops. And now we are going to go back into here. We're going to configure this, and we're going to change this over to I, and it will readjust things to where this is Q. And so now, and we'll give it 10 bytes. So now this is actually set up kind of a two-way communication. On the main CPU, you will have access to this data via via the inputs and outputs, and you'll have 10 bytes going back and forth. I'll show you that. So input 10 bytes starting at 2.0 Q1. So locally it's going to start at Q 1.0. So this is on the edge, and that's how this sets up. Now you could absolutely go through and use like puts and gets and do all of that. But what happens is, instead of having globally addressed memory, you would have to set up a data block and kind of do this on the back side and set up everything manual. If you're just wanting to quickly set up a couple and send back and forth a couple of bits and bytes, then here's how you do that. You just set up this transfer area and it starts transferring it back and forth. And one thing on this, because we're working with 2 different processors, you want to right click on each processor And we could do it from this screen too. So right click on each processor, compile hardware, rebuild all, because we have two different processors. So right click, hardware, compile, hardware, rebuild all. So, and then now those addresses will be available. So let's go into our Edge PLC. And the way we would access this memory is pretty well straightforward. We can make tags, PLC tags, go to our default tag table, and we can make our, so if we know this is on the edge, so input, input DI1, for example, be a Boolean. Not going to be that address, right? It's going to be, it started at address 1.0, and that's it. And if we wanted, so we call this main input, yeah, 1. In tags, obviously you can use spaces, no problem, because it'll just create the quotation marks around it. So let's main. And maybe this is like two main. One. Maybe that's a way to think about it. And we're going to change this to a Q. And we're going to name it Q 1.0. Okay. So however you need to think this from main, so, and this is how you would access it. And on the other side, you would just create your tags based on that. Now, it's not perfect, but it is a lot easier than going through and using like puts and gets and setting up data blocks and all of that stuff. So fairly simple on that. And yeah, that would be, and you can kind of go from there. You could create logic from within your processor to activate and use those bits and bytes however you would want. Now, remember, if you were to do like a 2 real one, let's see what it does. Obviously it doesn't like that, so you're gonna have to do Q maybe W. We'll see how. I didn't do this. I don't think QW. We're gonna have to start at minimum 2.0. That doesn't work. Do DW. Oh, maybe it's I'm dumb. It's just Q. Anybody knows how to do this? Yeah, so how would this do this? Expected value RD. Yeah, syntax error at character 3. Yeah. QD. Yeah, that's it. I knew, because a real value takes up 4, so it's going to be Q double. So it's a double word. So you have words, double words. Yeah. So that's where we go there. So a real would take up a double, so QD2, and then our next available would be QD6, right? 2, 3, 4, 5, 6. Yep. So 2 to 3, 4, 5, 6. Yes. So 6 would be the next available. Always confused. I don't know about you guys. Sometimes, like, does it include the first one? Does it include the last one? That's why I always gotta like count stuff out. So don't feel bad about struggling with some of this stuff, because it's, yeah, sometimes you use, especially if you're going from what's it called, like pointers, like you use the W designation a lot, W. So like DB word, so like DBW, DBD, like all of those. So that's what's going on here. So just know that if you're using a reel, you're gonna have to use this type of setup. And yeah, but that's on the other side. You would have access to the from edge would be coming in on the inputs. From main here is coming on. So to edge, from edge, same concept. Just whatever you do, pick something and stick with it. Whether you're using the to from designation, because it isn't 100% set up for you. It gives you the flexibility, and honestly, that's kind of what Siemens likes to do. They like to give a they like to actually give a yeah, give you the flexibility to do whatever, but then kind of complicates it a little bit sometimes. But that kind of goes back to what I was saying earlier about having that hardware level understanding of, like, from this, like the little Arduino stuff, being able to work with your hardware, and you'll understand why things are done a little bit better in Siemens. Like, for example, we'll transition to the next little topic here. I might actually be able to do 2 hours today. The past couple of streams have been running up into 3 hours and been wearing me out. I'm sure it's given you a lot to like help you get to sleep with at night. But yeah, today we're gonna talk about another one of these topics that are like kind of entry level, but sometimes you just learn it and you don't really understand why. But we're gonna talk about like different integer values, and I'm gonna want to get this up to speed. Does this work? Yeah. So different values for integers. For example, if we were to bring in our, look at the analog input on this device. Oh yeah, see, yeah, for you it is the weekend. I'm trying to make it to the weekend. My boss never lets me stop working. So, by the way, my boss is me. I won't give myself a break, but yeah, welcome to the weekend, Saif. I hope you have great things planned. Great things planned for you. So yeah, so let's look at something here. We were on our basic system. Whoa. Let's look at this, the IO. So if we click on our device, go to properties, and then IO tags, it will show you kind of all of our IO that's available on that. So the integers here are the analog inputs. So we have these input words, IW. That's where I get the W, DW, all of this. So anyway, so you have an input word, so 16 bits. Okay. Well, 16 bits, that's in a word, right? So I'm going to name this analog 1. And apparently, as Brandon was trying to distract me earlier, he's like, you need to watch out how you abbreviate analog. Just yeah. But yeah, so we're gonna call analog 1. And then now I want to, what we would actually do is, let me go 1 second. Let me plug in this PLC and see if we can get it connected. So this may or may not work. So, got this. So let's see if we can get this thing connected. So I did this on that video, and so maybe I remember what devices it was, but if not, we'll just use this. So if you have never used updated or online access, all I'm doing is this goes out and scans whatever it can see for like PLCs, HMIs, things like that. And so I just turned on this little guy here. I don't think the .1 is gonna work. So let's look. So I'm gonna go back to my network. Look at these. So it needs to be .4 in order for it to work. So what I'm gonna do is I'm gonna go here to online and diagnostics. Double click there. Of course it's trusted. It's me. And we're gonna go to functions. Just making sure that is A40. Yeah, oh, it's running. So I'm gonna go to assign IP address, and then I'm gonna go to 4. Assign IP. And why you no set? There we go. Can't be running. Learned that today. Hey, we all learned stuff. That's awesome. So now, in order to actually go to this now, let's connect. So I just went through and the reason it kind of went offline is because it changed the IP address. That, and then start search. Should be able to pull this up. So, yeah, kind of just relaxed going through. I'm gonna go online with that. Of course, it's trusted. So now I'm online with this, but obviously I've got a bunch of yeah, because I've got the stuff from that. So let's just download this. So we got to be offline if we want to do just a full download. All these little things that become kind of continue without synchronization. We're gonna do a consistent download. We're gonna load it. It's still not running right now. Oh, I want to show y'all something, because one thing that I'm going to say no action because I'm about to do another download. If you are working with a Siemens PLC and you're kind of getting stuff started up, and I've talked about this before a good bit, go to in your properties of your PLC, and this is for all different types of PLC. So just click on your PLC, go to startup, and this is 60 seconds. Change this to 10,000. So like 10 seconds, or maybe even like 5 seconds, because this is just a delay before it actually transitions into run. And so like it can get really annoying sitting there waiting for that, and for some reason it says that it waits 60 seconds, or default is 60 seconds to wait. So let's change that. Let's download again. And again, it will do a quick compile before you download. But yeah, just doing that. And then now on this, start modules. Yeah, so I want to go ahead and start this module and then finish. And then it'll actually do it. And then click, 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 and it doesn't like something, but whatever. So now we can go online with it, because we want to talk about these analog inputs, right? And so I want to, I just want to make a temp, or yeah, temp word. and I want to, just because I want to show y'all some stuff. I don't think I'm going to, so we're just going to put in a move block. And then we're going to just move this analog 1 into our temp word. Okay. Is there an explicit conversion there? No, we're good. All right, so save, download. We're going to go online and watch this. Because we want to talk about some things. I'll close that. Because this like catches some people off guard. And again, going back to, of course, it's going to show 0 right now. But I'm going to pull this down onto this other screen. We're going to do this because I want to talk about kind of the, and I need to forgot to turn on my pen. I haven't set up anything for this live stream. I think I need the weekend. I think it needs to be the weekend. It might be the weekend after this stream. So what I wanted to talk to y'all about was if you aren't used to scaling the inputs on this, and what I mean is this value here that comes in on this is going to be some big number. Now, normally it's not going to be like 0 to 100%. You want it to be 0 to 100%, but you need to be able to scale it. Now, in order to scale something, you need to know what the minimum is and the maximum. And I know y'all know all this, but there's a couple of intricacies to this. So like 0 to 100, what does it equal to on this input? And if you know, you can throw it into the chat. But like, depending on what type of processor you are used to using, that number will be different. So, and sometimes it doesn't quite make sense why that number is what it is. Well, you might go through and you might be well enough aware that, oh, hey, this is got to be this has got to be some sort of like value that's some sort of base 2 power, right? Well, we looked at earlier, we know that it's a word, right? So 0, there's 16 bits in a word. So we might think that this value is 2 to the 16, right? So that's 65,536. And we say, no, that's not quite right. Because that's definitely not going to be it. In any circumstance, it's not going to be that, because this value normally is going to be able to have a sign to it. Like, especially on an analog input, you might have like a negative 10 to 10 volt analog input. So you need a negative. And so, all right, well, that takes away, that sign bit is usually the most significant bit. So that takes away that. So we might say, okay, it's 2 to the 15. Okay, 32,768. Okay, that's cool. But it's not that. It is not 32,768. So 0 to 100, this upper limit here, we're trying to figure this out. And we know a word equals 16 bits. So 1 minus 1 for the sign leaves us with 15. Well, if you're familiar with what this is on a so all right, let's go down one more, because it's not 32 620 or 768. So let's do 2 to the 14. 16384. Now, if you're familiar with drives, and we're going to talk about this, that number should kind of like buzz in your head a little bit, because that's the number that's 100% for a drive, like a drive set point that's going out to a drive. That's the number that's 100% for it, but it's not for these analog inputs. And turns out that it is 27348, just random. 27348. And what is that? Well, let's look at what so let's do it this way. So let's look at 2 to the 15 would be 32 768. So that would be max if it was the full 15 bits. See, if 100% was a full 15 bits. Well, let's take that number, copy that, then 27 348 divided by that, you get like 85%. I may be wrong on the last part of that, but it's around 85% of what it actually is. So what this is doing is, the reason it's not the full range is because you actually want to be able to know if you were over 100%. And so this value here, actually gives you the ability for the system to see up to 115%. Okay, and below 115%. So like if you were on the negative side, so plus minus 115%. Now that's pretty cool, because like it's pretty important to know if your pressure is just a little bit over your range. You know, like you might be reading on your value just a little bit high. So like 103% or 101%. You might be reading a little bit high there. But if you tapped out and this value was the full maximum range, that 32,000 number, if it was tapped out, then you wouldn't know the difference between 101% and 110%, which could be a significant difference. And so the Siemens analog value here that you get, if you wanted to scale this to a what's it called, a percent, you could take in that upper level, so you can take that upper level, and all you're just going to convert this into a real so you can divide it. So let's do that real quick. So we're conversion operations, convert, and I'll show you. We're going to do we'll do int to real, because an int doesn't have that first side. And then we'll just move this over here, and then we'll give it an output doesn't like that because the word. So we do this. We do temp real. Like the fact that that's. Now we'll just divide by our maximum. So we can just. And now one thing that you could do, so if you divide by the absolute maximum, so 27, what number did I say? See, I always forget these things. Again, 27,348. And I don't even think that's right. I think I'm combining the two. If I'm wrong on that and you're in the chat, yell at me, please. So 27, 340. Not 0. So let me do one quick thing. Because 32, 32, 7, 8 0.85. That's not right. I've got something mixed up. I'm mixing up some of my numbers, but anyway, one of the things, if you put that in, you will get a number that's a decimal. So like 10% will be 0.1, 20% will be 0.2, 50% will be 0.5. So we want to move that. We want to move that by like 100 to 2 decimal places. So you can either go through divide and then multiply, or just change this and move the decimal place 1. So it's there. You go 1, 2. Put it there, delete that decimal. We just multiply by 100. So, and then your output will be the scaled value. So we'll download this. Mm-hmm. $27,648. Oh, that's what I've done. It's supposed to be 27. $648. Oh, that's interesting. So, looking at what this 85%, so the maximum detectable for that value on the on that card is 32,511, not the actual max range. So we're learning about these things, because the 32,767, 768 value is the overflow value. So that's, you don't want to overflow. So, yep. All right. All that to say, here's how you scale it. So you're scaling to 27,648, and that logic right there, I mean, that's it. That's your scale function. And you could do it a little bit easier if you had a value that was like written in SEL or something like that and did kind of like an implicit conversion. You could do it nice, easy on one line. There's also scale functions and scale values and everything, but like if you were to actually want to, like if this had a minimum value, this is 0 to 100. Say the value is 0 to or sorry, like 4 to 100, then you'd add in that offset, and so you'd have to do an addition at that point. So that's a little about analog inputs. Now the same thing, and we talked about that before, that on a drive, this same concept of having the ability to go over 100% is available in a drive. Now, the hardware component, the reason this whole thing is kind of based off of not the max ranges is because of the physical hardware. You're not wanting to saturate, you're not wanting to overflow, you're not wanting to get into this situation to where you have this a problem based on an analog input coming in, it overflowing, and then a PID controller like going crazy. Well, in a set point for a drive, we said is going to be that the 100% mark is going to be that 2 to the 14 number, because sine plus minus is the 16th. The 15th bit allows you to actually command up to 200%, or the value can actually read up to 200%. So kind of getting back to the drive sort of like methodology and thought process, when you command a set point speed, you can command, like if you want to run over 60 hertz, you can absolutely go over 60 hertz. So like if you wanted to do, or I guess everyone else is 50 hertz. Sorry, sorry. Most everybody in here is international, but yeah, here in the US, if you want to go 60 hertz, then you would command that 100%. So that 16384. Well, if you want to go 66 hertz, you could actually command 10% over. And so you could actually command 1.1, you could put a value of 18,022 in there, and it will try to run at 66 hertz. Now, if your rated speed is 1750 times 1.1, what does that get us? 1925. So the default settings on a Siemens drive with this 10% overspeed is going to run up against the maximum speed of the motor, the default. So the parameter, I want to say it's 1821, maybe check to see if I'm right. Like if next time you're in Portal or start drive, look up parameter 1821 and tell me if I'm right on if that's the motor maximum speed. But that by default for a 4-pole motor 60 hertz is going to be set to 1800. So it's kind of the 4-pole ideal value. Well, I normally go ahead and bump everything up to the maximum motor speed to be 2000 hertz, because you don't lose a lot of torque by going over speed just a little bit. But if you do want to get a little bit more speed out and you got a little bit of extra torque available in your motor, then all you would have to do is, in this case, if you wanted to go 110% speed, then if you wanted to go that 1900 RPM, then you would just type in that, or you would just send over that 18,000-ish setting. So you just send 110% over in your set point. So that's where those numbers come from. The 16,000 number that we always see, like the 16,384, that number that I keep getting like the 384 in my head. That 16,384 has a purpose and has a reason. And you can absolutely just give your speed set point to a drive. You can give it up to 200%, because remember that bit that you're kind of like throwing away, that 15th bit, it doubles. It doubles your that values, because if you didn't watch the kind of like introduction to digital logic and embedded systems, we kind of talked about the number schemes. And if you're not familiar with how binary numbers work, each bit doubles the last bit because it's base 2. So it's times 2, times 2, times 2, times 2. And so if 14 bits is 16,384, then double the next bit will give us 32,000 whatever, 32,762 or whatever, 768. And so, because you're just doubling it every time. So using that, you can go up to 200% speed. But in a drive, if you want to do that, there is that max motor speed that caps you off. Like, no matter what you command it, it'll cap you off at your motor speed. Just the same way that you have another controller that caps you off at a maximum current or maximum torque. So, same stuff there. So, we are at almost exactly 2 hours. I'm just tempted because I found some really cool stuff on DCCs, but I don't know if I want to go full drive at the end of this one. I don't know if you're one of the like people that are actually in. So we got 5 people in here. Y'all throw in chat if you want me to go into extra DCC stuff. Because yeah, you know how much I love drives, and if I love talking about them. Oh, Ethiopia, that is new. Welcome from Ethiopia. If this is your first time, it's awesome having you here. And yeah, we just went through a whole series, a whole 2 hours talking about S7-1200s, and I'm a drives guy. If you're new to the channel, I'm a drives guy. And so, so I will say in starting out in high school, if you're already like realizing in high school that automation is the path to go, like, you are well ahead. And honestly, the best way from my perspective to be attractive is take care of yourself, and that's physically and then mentally, and treat yourself well. And so, like, the fact that you're already kind of talking about the automation and getting into automation, then yeah, sounds like you're wanting to improve yourself. And like, not everything's about money. If you're kind of a jerk in life, no one's eventually gonna want to be around you. Younger, I was more of a jerk than I am now, but yeah, it also helps. It also helps if you can, like, I don't know, bench press more than your weight. Set that a goal. Like, that's pretty easy, especially if you're still in high school. You should be able to bench press your weight. Like, that's kind of a goal. But yeah, so if y'all are wanting to go through and talk a little bit longer, I want to show y'all want to hang around. This is a little bit more deep dive. So far we've been talking about like the basic automation stuff, and so I'll spend just a couple of moments kind of rehashing something that we talked about on the last live stream, and kind of going through, and let me get this pulled up, because last week we were talking about DCCs, which, if you don't know what DCCs are, you're probably like most people. Look up last week's live stream, and you will learn about that. But you will need to know about drives. If you don't know what a drive is, then drives move the world. They are the interface between electric motors and yeah, the control system. So I will pull up this, and here's kind of where we left off last week with our kind of just drive control charts. And I had another kind of person asking about how to use a PID in DCCs, and this kind of goes into a so much higher level of control that's available in the S120. And so if you've already invested into an S120 system, this goes to show you, just with a little bit more, you have the ability to do a ton of control. Because I just pulled in out of the closed loop control box. We have some really cool functions here. Someone asked about a PID. So we have a PI controller. So what you have in your like speed controller is a PI controller, and they have a built-in block in the kind of standard library that you have available here. And I'll bring up the help file. That's not for that. That's for something else I want to talk about. So let's talk about the PI controller. And let's go through this help file. Let me move my face up here, because I know y'all want to be personal, you know? Not all of these. I love all the content out there, but just watching screen captures and somebody talking about a screen capture, I don't know, it kind of bores me. But let's talk about what is available in this what's called the PI controller is built into DCC. So just drag this in, and the inputs that we have here kind of shows you the block, and it kind of details out set points, actual values, pre-controller, blah blah blah, all of that. And again, it kind of goes back to, if you don't know how to use to troubleshoot or read one of these functions, block diagrams. Let me bring you down onto this screen and swap back to my sketch pad so that we could talk about like how to read one of these diagrams, because this is very important, especially if you're doing with drives, because any control system that's actually going to be controlling has set points, feedback, some sort of control actuation. And a PI controller, this is a pretty simple control block diagram for it. And if you start getting into drives, you will need to eventually, if you're wanting to kind of like separate yourself out, you're going to want to know how to like read these block diagrams. So let's take a moment to just kind of look at what's going on here. Any sort of feedback control system, you're going to have a set point, and you are going to have an actual value. Okay. And then you're going to subtract. So you're going to create what's called an error signal. And so, like in life, we have feedback controls. Yes. So kind of like in life, we're kind of talking earlier about True Sparks here. He was kind of talking about how to get ahead in different areas of your life. You have someplace you want to be, okay? And you look at where you are. That's what this is. And you figure out, how far off am I? So in my bench press reference, our set point for me, it'd be 165 pounds. So, and I look at my max is 150 pound max. And so my error signal in this case would be 15 pounds. And so this is a control system, is like, you can kind of think about things in life. Like your error signal here is, I need to increase my bench max by 15 pounds. Now, how do I do that? Well, because I have this error, I have some sort of control system. In a weight room, I mean, that could be any number of things, like different things. Like in this case, it might be, I need to work on my negative reps. I might need to increase my protein. Maybe I need to get more sleep. These are all kind of the parameters that are going into this control system. And then the output will be my work. Never thought that you'd be talking about drives and working out at the same time. But these feedback systems are kind of the same. I mean, they're everywhere. They're not just in automation. So, and then you take and you look back at your actual value after your work, and next thing you know, you're at 160 pound bench max. And so now your error signal goes down to 5 pounds. And then so you go through your program and you get your feedback. So that is a weight room control system. And that's how you can kind of like think about, like in real world terms, what an automation and what a control system is. You have some sort of desired goal, a set point. You have your actual value, like where you actually are. And then it creates this signal that you're trying to get your errors to 0, right? Because in a weight room, you say once you meet that goal, that set point goal of 165 pounds, maybe the next thing is I want to do 2 plates on my bench max. So I change that to 225 and go from there. In our control system, the set point is going to be changing constantly. And it might not be, but we're probably going to be changing our set point. And a set point doesn't have to be speed, it doesn't have to be position, it doesn't have to be pressure, it could be anything. And so control systems are more than just drives. It's just that drives are cool or something. So let's look at this block diagram and how to kind of trace through it. So in this PI controller that we have in our DCC chart, we have 2 inputs. So these are our set points. So it's kind of cool. It has 2 inputs, W1 and W2, that are set point inputs. And they come in and they get subtracted by our actual value to create our error signal going into this little block here. So if you notice, I'm going to clear this out. You have this YE value here, an error. And so our feedback set points, so these are set points, these are our feedback, and then our error signal is right here. And if you notice, this goes 2 places. It goes into this little block, and then it also comes down and feeds out here. Okay? So, we have that. So let's clear this out. So that's kind of the way that you're looking at this. You're looking at just like an electrical diagram, just like you're looking at a wiring diagram or something. This is the same thought process. You're just tracing it through. So clear that. We have 2 different controllers. We have a P component, which if you're familiar with a PI controller, it's the P part of it. And then we have the I controller. Oh, I know, this is groundbreaking. We have our I controller. So that's here. So if you're familiar with PIDs, then you're understand in this type of controller, we don't have that derivative action. And so we don't have the derivative portion. We just have the proportional and the integral. And so you can see those here. You have some options here that you can turn on and off different action, because at the end you take, there's this summing block, which by the way, in control diagrams, if you have a circle with arrows pointing at it, that's either a sum or an addition. And so that's a summing block. And if you sum a negative, it's a subtraction. So kind of over on this side, you can see what's going on here because of that. So, get off of there. So that's summing block there. So if you notice, you have your I component is here, and it goes up to this summing block, and then your P comes from here and then comes up this summing block. And then you also have this other line here that they call, what do they call this? Oh, it. By they, I mean the Germans. What's WP? Pre-controller value. Oh yeah, we talked about that last week, didn't we? Huh. What are the odds? Bangladesh. Awesome. Awesome, awesome. Welcome to the stream. I know the stream at this point has completely diverged. We did 2 hours of PLCs, and now we're getting into the fun stuff again, and we're talking about DCCs and S120s. But we're talking about this PID controller block in DCCs. So we see that we have this pre-controller values, and like I said, we talked about what pre-control, another name, get rid of that last L. Pre-control is, it's, hey, I know I'm going to require this much to get something moving, or get my set point to, or my actual value to change. I know I'm going to require that this much work, so I'm going to go ahead and just inject that in to the output. So kind of the same way that we had our speed, like speed set point going in, and then from this thing we have torque coming out, and we have our torque pre-control, and then we did the same thing for inertia compensation last week. It has this built into it, so it's pretty cool, pretty awesome stuff there. So yeah, so the thing about it and what makes this really cool is because of this function, you can do some pretty cool things even with like pressure control, because the CU320 has analog inputs built into it. So you can actually bring in analog inputs from like a pressure transducer or something like that, and use this function, use these PI controllers just the same way as you would. Just the same way as you would make a controller like on a PLC, and you're kind of doing it all down at this like really fast, like 250 microsecond update time. So really tight control. One of the things that you'd also could possibly do with this is like do hydraulic pressure control like that, and thinking about hydraulic positioners, a lot of it would have to do with pressure. And so you have a built-in position controller in this thing, and so you could add in pressure control and all this. So really cool stuff that you could do built in on the DCCs. So last thing I'm going to talk about today, because we've touched on it again, inertia compensation. And I think we had a little bit fun time talking about what inertia comp is in a system. And if you missed that, go back and watch last week's stream, because I went into a lot more detail on it. But one of the kind of real quick view of what inertia compensation is if you have a big drive system, a big heavy object that you're trying to move with a small kind of like gearing, you're going to have a lot of inertia. And if you know that you're going to have to put out so much torque in order to move something, to push against something to get it moving, you can go ahead and inject that torque into the controller so that your speed controller doesn't get what's called saturated. Again, watch last week's live stream and talk about it really in depth. But one thing I didn't really talk about, and I'd honestly kind of like how the mechanism works, is in a fixed acceleration system, you have a known, like in a ramp function generator, the ramp function looks something like this, right? And with this is your set point, speed, and then this is your kind of acceleration time, and deceleration time, right? That's, if you're drives people, you're used to kind of seeing that stuff. Well, the way an inertia compensation works is, remember, we're trying to inject the accelerating torque. So there's a change in speed here that we are trying to create. Well, in math terms, we kind of start talking about calculus. And if you haven't done calculus, then you're kind of at a disadvantage in these conversations. And we were kind of talking about before whether or not it would be worth to go to a university. One good thing about getting a degree is that you are kind of forced to do these hard math stuff like calculus. And it kind of gives you a foundation to be able to have this sort of conversation, to really understand why something does what it does. And so it kind of takes you to the next level. So to be an automation engineer, you really just need to learn how to learn. But like, this conversation is a physics conversation, not really an engineering conversation. But you'll find out that if you have a really good understanding of physics, you're going to be a lot better off in moving things. And and so you're trying to create this change in speed, and which that's called an acceleration. And if you've done calculus and you've done physics, you know that there's relationships between speed, acceleration, position. And if you have an acceleration and you start doing integrals, you will step through and start getting equations that look a lot like the equations for motion in physics. And so the first thing you do in physics is you learn this equation, like if I were to drop this pin, how long does it take in order to hit the ground? Well, you have all these equations that you memorize if you don't know calculus. But if you do know calculus, you start with the acceleration due to gravity and go from there. Well, you start with 9.8 meters per second and go from there. You take the integral of it and you create these kind of relationships that go from that are tying into the physics. Well, from speed to get acceleration, you take the derivative. And so you get this acceleration component. You take the derivative of this equation, you get the acceleration of that motion. So and if you really want to be a nerd, just call someone a third derivative, because after acceleration, if you take the third derivative, you get the jerk, and it's a real thing. And so if you just secretly call someone, not your boss or your wife, but yeah, call them a third derivative, and they'll look at you, and then you'll realize how big of a nerd you are. Anyway, all that to say, if you want to know what this acceleration is, there's a couple of different ways that you can do it. You can do so change in speed over change in time is going to be the slope of a line. Well, the acceleration is, the derivative is a fancy slope of a line. If this is a constant speed, then it's just the slope. So rise over run. Well, if you were to just have a constant acceleration, this would be pretty easy to create a feed forward, so inertia compensation. Well, what happens if instead of your acceleration curve it looking like this, your set point looks like this? What if it looks like this? What if it's constantly changing? Well, what's the slope here? The slope is going to be very different than the slope here. And this gets into a calculus problem. And so at this point, you would want, if this is t, and this is speed, you would want a dn over dt. So you'd want like a speed over time. Well, guess what? There is a block or a derivative block. And it is right here. Haha. So you can actually go through and create your own variable output inertia compensation. And the pre-control block kind of does this on its own. It has this kind of an action in it. It's taking this derivative because it knows, hey, if I'm accelerating that. But this is a block that you can actually use to be able to create that kind of feed forward. And you need a derivative because the derivative, this derivative action, derivative, how do I spell it? Spelling is hard. V-A-T-I-V-E, derivative equals the acceleration of whatever you are doing. So if you're in speed, so if you're in speed, it's the acceleration. So the change in speed. So now it's not necessarily always the acceleration, but it's kind of the way to think about it. Because if you're talking about a position, the derivative of position is actually speed. So it's the change in position. So what's the change in position? How fast you change your position in a given period of time is speed, so velocity. And so, yeah, velocity, I guess, is a better term because, yeah, anyway. And then if you take the derivative of the acceleration, it is how fast is your acceleration changing? And that is a component that is kind of intuitively you understand, but it's really hard to kind of think about like what it actually is. And that is the third derivative, the jerk of your equation. And if you've done technology objects or anything like that, you've seen that like jerk limiting. And what that does, the way that you can think about it is, imagine if you were on an elevator, or actually, okay. Yeah. So imagine if you're on an elevator and you were to, slowly start accelerating up. So your acceleration goes from 0 to slightly and then goes up and just kind of smoothly goes up. You would hardly kind of feel that acceleration. But if you were to really like go from 0 to accelerating at max speed, you would kind of get pulled down into it. You would get jerked. Same thing as if you were putting brakes on your car and you're coming to a stop. You have some sort of negative acceleration, okay? Yes, soft starter would solve the problem. It would definitely move it. But yeah, so if you're kind of driving along in your car and you kind of press on the brakes and you're coming to a stop and you just hold that position on the brake, when you come to a complete stop, you kind of go, you kind of like pop forward because you're going from once you actually hit the stop, your acceleration is going from like, say negative 3 meters a second or something like that, or negative 2 meters a second. So your acceleration is negative 2 meters a second and it goes to 0 almost instantly. And so your jerk on that would be incredibly high because the change in time or the change in acceleration going from negative 2 to 0 in almost no time makes for a really high jerk. So if you've ever done this, you kind of like, as you're coming to a stop, you kind of let off the brake a little bit and it smooths it out and you don't get like lurched forward into the seat. So that's kind of a practical example of what jerk is. Well, this derivative action, this derivative block here, you can start doing some pretty cool things to smooth out like your drive system by kind of like smoothing out the jerk and smoothing out the acceleration, because you could start injecting these set points based on derivatives and based on integrals as well. And so yeah, I mean, I just wanted to show y'all that a little bit, kind of totally off topic towards the end. We'll try to get back to maybe some more in-depth drive topics next week. But yeah, so glad everyone that has been on has been, you kind of got 2 hours of PLC content and then about 30 minutes of fun of your drive and everything. But yeah, so yeah, if anybody that's online, thank y'all so much for making it through all the content and being part of this channel. The fact that we're kind of growing and we have so many different faces from different parts of the world, all kind of talking about the same thing is really cool, and kind of a lighthearted example of working out in a gym and kind of like control systems and everything. But this is kind of a universal language, and anybody in anywhere in the world that is having to deal with these control systems can communicate. If you can cross the language barrier, you can definitely communicate in a control system. If you're doing automation anywhere, you're going to be having to come over and overcome the same problems. And so I find it very cool, and I'm so appreciative of everyone that takes part in these live streams and watches our videos. And just, we're growing. Good growth is sometimes slow, but I love the fact that more and more we see more and more on each one of these live streams, and all the videos are getting out to more and more people. And so just a last little comment, like, if you're not subscribed, please subscribe to the channel. It gets this content out to more people. Commenting on posts gets more attention by the YouTube algorithm, and it gets more people out there, because again, it's really not about like the dollars and cents of like being a YouTuber. It's us building a community, helping each other out, and yeah, just growing and getting this information out to more people. And for all of you that have been on this, I thank you, and thank you for your support. And yeah, so in the meantime, if there's something that like comes up in this kind of your world on a project or whatever, find a video that might be close, whatever, and comment on it, and I'll help you out. At the very beginning, when I didn't have a lot of videos, I would get kind of random comments and questions and kind of answer oddball, just unrelated topics on different comments into different things. So feel free to comment with your questions about not just Siemens control systems. Have a lot of experience with that, but if you're having trouble with something in your plant, that even if it's controlled by some other drive, some other manufacturer, at its core, it's a physics problem, it's a control system problem, and then you may have to fill in the blank of like how to actually execute that. But that's where everybody can grow from these streams, even if you're not using Siemens. So yeah, I appreciate it. Y'all have a great weekend, and yeah, we are just going to be, yeah, keep going. And again, as always, share these to your friends, share these to your coworkers, and if you have people that you work with, yeah, bring them in. I appreciate your time, and y'all have a great weekend. If you're in the US, stay warm. If you're not, and you're already warm, you're blessed, like, because it's cold here. But yeah, y'all take it easy. Y'all have a great weekend, and yeah, see y'all later.